Okay, I think we're live at the moment with the question and answer session. So I will first introduce myself. I'm Gunal Jahangirova. I work as a postdoctoral researcher at Software Institute, which is a part of Università della Svizzera Italiana in Lugano, Switzerland. And with me, I have two of our speakers. First is Michael Weiss, who is a PhD student at Università della Svizzera Italiana in Lugano, Switzerland, and Giuliano Mirabella, who is a research assistant at the Universitat di Sevilla. So you can type your questions in the chat and the speakers will answer them. So in the meanwhile, I will start with Michael. So Michael, in your presentation, you have this idea that we might sample training data using only a portion of it to calculate surprise adequacy. And the results show that for some portion, for half of the data, this works out well. And I think this introduces the new parameter, which is the sampling size. And do you think like you can give some recommendations of what size to use? Is it very case study dependent?
So as of now, we only have one case study, right? So I very much assume this to be case study dependent, but I don't know for sure. In MNIST, which as always is kind of the Hello World case study, right? We, for two of the sampling methods, including uniform sampling, we get very good results with 1/3 of the training set, which would be my recommendation now. Generally, the performance of surprise adequacy converges, right? So it is optimal at the full training set, but it converges eventually. So the recommendation isn't really that there's one specific sample size that you have to use, but you can really use the sample size as a trade-off value, right? Where you trade off prediction time versus kind of the performance of surprise adequacy.
Okay. Okay, there is one question in chat for Giuliano. So it's a question by Vincenzo Riccio, and it says, besides validity, can yours or a similar prediction model also predict whether test inputs are also similar to real ones? And by that, he means similarity to the ones produced by real users.
Yes, up to now, we have not worked with the kind of prediction or measurement. And we produced our dataset synthetically with a tool called ResTest.
Okay.
So we are still in progress to go and study and analyze if in a real scenario the approach will work out as well or not.
Okay. Thank you. Michael, there's a question for you. So your paper, it kind of is a refinement of an already existing approach. So the question here by Andrea Stocco is if you had a chance or are you planning to interact, collaborate with the authors of the original surprise adequacy paper?
Yeah, good question. It's what you would expect, right? However,
yes.
I really have to say that the surprise adequacy paper describes the approach really well, and with the reproduction package online, we really found all the information that we needed. So we didn't have to contact them specifically for our paper. That said, especially Shin, which is one of the co-authors of the original surprise adequacy paper, he gave a bunch of talks in the recent 2 years about papers or techniques where they themselves use surprise adequacy. And I think maybe unconsciously we learned a lot of lessons also from what he presented there, which was definitely helpful to conduct this study.
Okay. And there is a question for Giuliano, which is about input generation for API testing. And the question is if this approach would help with performing security testing, where you try various attacks. However, there has to be a sequence of events.
Okay, we think actually it would, because with our approach, it's supposed to, the percentage of validity of valid API requests is supposed to increase. So in a event sequence scenario where a validity of an action depends on the validity of a previous one, generating more valid requests with random generation would probably have as an outcome better performance of attacks and error detection. So we think so. We think it would help. However, we are still trying and studying further extents.
Okay, thank you. So if anyone has a follow-up on their questions, please print it in chat and I will ask. And I have one question for Michael. So in the paper, you have a research question that shows that surprise adequacy is sensitive to the training instability. Do you think this is something specific to surprise adequacy, or is this something all deep learning approaches that try to address the deep learning systems are prone to?
Well, as of now, I don't think it's only regarding surprise adequacy. I think there's even similar approaches that are based on this principle, right? If we, for example, think about deep ensembles, which are commonly used techniques to detect uncertainty, they kind of build on the fact that if you train multiple models the exact same way, using the exact same data, you will still get different models, and from the conversions you measure the uncertainty. Now, hence, I don't want to say anything without having the numbers about how other approaches perform, in how sensitive they are to those minor perturbations in the weights. It is, however, that's kind of the only thing that we want to say. It's clearly very high for surprise adequacy. And to me, the takeaway message is not so much that it might be higher than other approaches, but it is just that alone. It's high enough to potentially corrupt the outcomes of a scientific paper, but also of practical applications, right? Given the wide range of outputs that you can get, all other things equals. And we've seen that, in theory, it becomes very relevant. We've seen that surprise adequacy is actually used in a wide range of application, right? So it's definitely becoming a standard. It's becoming a very well-established metric. So we really want to say, if you use this standard, if you use this established metric, please rerun your experiments to actually get meaningful results.
Okay, one more question. So let's say if we do uniform sampling, that's also it's random, right? And do you think if we do that, the instability also sort of increases?
Yeah, well, I mean, we don't discuss this in the paper yet, but we did some preliminary experiments. There we haven't found something like this. I mean, we saw it if we took the sample size ridiculously small, right? If we would only talk like 5% of the data, then there's a high sensitivity. If we are at the 30% that we for MNIST now see as kind of a very good trade-off, very good threshold, we didn't observe much like this. At the same time, MNIST it's nicely polished. It's a beautiful data set from that sense. And I would assume that as soon as we get to a more challenging data set with more noise, with for some classes fewer data, there's probably going to be a higher sensitivity.
Okay, so we have a question in the chat which asks, how could you extend SA to take into account non-determinism? As I understand, your recommendation is just to rerun it many times. Do you think it is possible to address this other than doing reruns?
Honestly, I haven't thought about it. For me, reruns are kind of the natural way to do it. I think it's a standard way to do it. I think people are familiar with statistical tests or similar things, right? It would be very interesting to see if there's other approaches, and I think for that it might be very useful to see what's actually really causing, like which hyperparameters, which changes have which effect on this sensibility, and that's something that we are actually actively targeting at the moment as future work. Hopefully we'll learn some lessons there that will maybe even guide us to coming up with better approaches that don't something.
Okay, and there's one more question for you, which says MNIST includes images. Many other data sets are also populated with images, but do you plan on non-image data set? Do you expect similar results? I'm not even sure if surprise adequacy was applied itself to non-image data sets.
It actually was. I think I only skimmed the paper so far, but I think there was a paper released again by the original authors or part of the original authors, where they apply surprise adequacy, a new variant of surprise adequacy to other data. The definition of surprise adequacy as such is definitely applicable to a non-image domain. So it would definitely work. How much the results generalize, I want to make any claims that are not backed up by any numbers, but I see no reason as to why they would not as of now.
Okay, so I have some questions for Giuliano. So in your paper, you address the problems that when you are generating test inputs for APIs, there are some rules that they should satisfy, otherwise you generate test cases that are meaningless in a way. So are there any rule-based approaches to that? Because I would think that if you know that there is a rule for this API, are these rules summarized somewhere? Can you extract them and just use the rules? And if not, so if you can do that, do you really need deep learning for this problem or not?
Okay, the current workflow in the industry is to express those dependencies in API documentations, but with natural language, which leads to errors and ambiguity.
Okay.
Which is why we are studying the problem of automizing the extraction of those rules, or at least the prediction of the request validity, which is which is what this paper is about. So the problem of having a beautiful data set with all those rules satisfied is that in a real scenario, of course, we cannot take for granted that a user or typical user would request valid or invalid requests as we'd like to, or a balanced data set. So which is why we're now studying in a real scenario, or also where API resources are constrained and we cannot stress the service as we wanted to.
Okay, so my next question is, how did you generate your training data set? Because then I would imagine that you should have a labeled data set that says that these inputs are right, these are wrong. Was it like a manual process, or how did you go with that?
Yeah, we have a tool called ResTest, which gives us the capability of handle those constraints, those dependencies, with a specific language called IDL, interdependencies language, which was developed and studied and defined by same authors of ResTest, which are Alberto and my colleagues. And so ResTest gave us the chance to generate the data set handling those constraints, and it can also just generate as many invalid or invalid requests as you want. So you should only ask for something, and that's what we provide it to you. But of course, if I don't know, I'm not aware if there are also others technologies, or we can extract the data set with use ResTest.
And do you have to train for each case study separately?
Sorry?
Do you have to train for each case study separately, or you can have one model that works for different APIs?
No, the different APIs needs different models.
Okay.
Because of the number of input parameters is not always the same. The dimension of the first vector, the network can accept change. So the model is flexible, but it needs to be retrained on the.
Okay. And how long does it take to train this kind of model?
Well, since it's not a big, really full of, it's not like a convolutional neural network. So we have maybe the order of 3,000 of parameters. So it's quite quick. Okay. However, it's slower than, for example, random forest or any machine learning technique not based on the gradient descendant algorithm, which is the computational costs we pay for the network to learn.
Okay, so we have a question in the chat which asks what's next on your line of research. So I was thinking we could ask both of the speakers as a final question about that. So whoever wants to go first.
Brianna, you go ahead.
Okay, thanks. Well, we are studying now how to. We want to compare our technique with other machine learning techniques,
Okay.
Which I mentioned before, like random random forest and entropy-based decision trees. And this is our first line of research. We want to improve, and we would like also to extend our services for the experiment. And finally, we will try to really test our technique in a real scenario where generating random requests is always or almost always give us an output an invalid request. So the data set is not balanced and perfect and synthetic.
Okay, so we got one more question for you, which asks whether the model should be trained from scratch if there are any changes in the API.
It really should. It really should. Up to now, our current approach, it really should. Maybe if the changes don't interfere with input parameters of our query or something like that, maybe one could also avoid it. But yeah.
Okay, now Michael, you tell us about your future plans for this work.
Yeah, right. I mean, many of the things we're planning to do are quite obvious from the paper, right? So we absolutely need more case studies. MNIST, I think, is an important hell of a role, but it's only a hell of a role. Then all of us who've ever written any code know that the minute after you deploy the code, you have some ideas on how you can improve them. So there's already the next propositions for further algorithm preserving performance improvements on our agenda.
Okay.
And then I briefly mentioned this before, and I think that will take a very big importance, is that we really dive into this question of sensitivity, right? So now we identify that the outputs are largely dependent on the random influences during training, but we want to narrow this down. We want to really essentially go down all the questions that have been asked before. How dependent is it on the case study? How does it compare to other models, for example? What can we do against it? Are the different variances of surprise adequacy differently susceptible to this? So at the moment, it looks like LSA is actually more sensitive to this random noise than DSA. And we want to compare all of this. And then also, I mentioned before that there's already novel versions of surprise adequacy proposed. And ideally, we also pack those in. So you'll see there's already plenty of roads to go.
I see. Well, good then. Giuliano, there is a follow-up. It asks, if the model needs to be retrained, how do you check for regressions?
Okay, so one chance could be to try the model without retraining it on the new data set, on the new API. And if the performance is lower than the expected, it's supposed to be an error, or maybe developers introduce an error. However, every time you train a model in such a data set we have, if the following logic rules, there is no space for ambiguity. So if the model performance is not high, there's been some kind of errors, and there's something we should just think of.
Okay, so I think there are no further questions, and the session actually is almost over, so we have only 35 seconds going. So thanks a lot for your talks, for the time you've spent writing the paper, making the video, and for being here and answering the questions. I hope whatever future work we have planned will go smoothly. Yeah, thank you.